Great. Does this? Yeah, this is good. I think Sotiris took my microphone. Okay, so Martin has already introduced me. I've been with UK Power Networks since July last year, and I've been in charge of the commercial arrangements for flexible plug and play. So it's essentially what we're gathered here today to talk about. My idea is to spend 20-25 minutes talking about who our customers are, so you get an idea of who the people that we've been working with are. We'll talk about curtailment and what drives curtailment, and kind of understand why we need a commercial arrangements work stream. So a whole 6 or 8 months now just thinking about how do we put this offer in paper. We'll talk about principles of access, which is essentially the rules for curtailment, and the commercial packages that we analyzed and considered, and how we came to our decision and our flexible plug-and-play commercial solution. Finally, I'll just kind of go through what our biggest challenges have been and the next steps that we have ahead of us. Okay, so Sotiris has explained generally what the technical problem is. And just so you have an idea, all of our customers that we approached last year are all wind farms in the trial area. So I guess the first thing about our customers is that they're seeking connections. So they're seeking to build generation plants in the trial area. And they are all getting connections because it's a constrained part of the network. They are essentially getting connections that are very expensive. Now, here on the table, you can see we have 6 developers. The size of the wind farms range from a 500 kilowatt wind turbine up to a 10 megawatt wind farm. And all of their connections are above 1.2 million pounds. Now, the reason for that, as Sotiris explained, is that because the network is constrained, they receive their minimum cost scheme connection, which essentially connects them to another part of the network. That is either through a sole use asset line that is more than 10 kilometers away, or to a higher voltage in the network. As Sotiris also mentioned, we've been proactive in our stakeholder engagement. So we found these developers, we approached them, we discussed our project, and kind of gave them an idea of the technical solution that we have. And we wanted to keep the whole process within the existing connection process, because one of the key things about all the Low Carbon Network Fund projects is that we try new things, but that we embed them into the business. So we make it business as usual way. So one of the things that we've tried to do is interact with our connections team and kind of understand the normal connection process, and we have been able to get our offers out in a normal connection way. And finally, we understand that we need to understand the benefits for our customers so we can convince them that we have an alternative that is attractive to them. Now, Sotiris said keep the concept of curtailment in mind, and I think this is just kind of a basic understanding of curtailment, because when we talk to all of our customers, the big question is, well, how much am I going to get curtailed? And that's kind of the one question. And to come up with that answer, and for us to be able to work with smarter grid solutions and be able to actually model and understand the levels of curtailment, there are essentially, in broad terms, 3 or 4 things that drive curtailment. The first one is the network topology. Now, it just means what does the network look like and how does the power flow in that part of the network that you're looking at, and what are the constraints. So if there is a transformer that has a limit, it's key to understand what that limit is and see when you reach that limit. some of the smart solutions have to do with accounting for variables such as temperature or weather. So it's external drivers like that that could also play a key role in understanding how much curtailment will you be expecting. And then finally, the two bottom ones are demand and generation. So the more generation that feeds into the network, the more likely you are to reach the operational limits. And obviously, the more generation, then it might be closer to those limits, and then hence our customers would maybe get curtailed more. However, if there's more demand and there's somebody using that electricity at a given point in time, then curtailment can decrease. So that's just kind of to get our heads around what drives curtailment. Now, that's all fine, and we can probably maybe convince somebody to, we're going to give you a cheaper connection just because it's closer to the network. However, you'll have to connect to active network management and get curtailed. And maybe they will accept. However, more of an operational concept and which drives us to the commercial complexity of this problem is that what happens if you have 2 generators or 3? And in a given moment, you have each 2 generators, and each of them are, in a given moment, generating 3 megawatt hours. And at that time, you've exceeded your limit for 1 megawatt hour. And that's fine. You've got these customers to say that it's okay for you to reduce their output. But what happens? You just need 1 megawatt hour. How do you decide which one? Should you take it from one of the generators? Should you take half and half? And so it's then that we understand that we can't just connect people interruptibly unless we set out the rules up front and we tell them this is how we will deal with curtailment and this is how we will manage it. So the concept of principles of access arises, and it essentially means what is the order of curtailment? So how are you going to curtail these generators? And there's many theories about this, but we essentially looked at 2 that are probably the most straightforward. The first one is last in, first out. So that just essentially means on a first come, first served basis, let's curtail generators. So the first one who comes is guaranteed that if anyone comes after, the second generator will get curtailed first. And so in that graph, you can see that generator 3 is getting curtailed down to 0, then the second generator, and then the first generator doesn't experience any curtailment. It has some benefits and some, and the other alternatives have their own benefits, which we'll talk about then. The second one is pro rata. So can we curtail everyone equally? And so equally in this case for us means proportional to what each generator is generating at a given point in time. Now, what we've done, and there's an extensive report which you can have a copy of, we've analyzed these alternatives and then put some commercial packages to implement them, and we've assessed them against a certain 5 criteria. The first thing that we consider to evaluate them, because obviously none of them are the answer, and there's not one right or wrong answer to this problem. But we had to kind of look at the pros and cons. So the first thing we looked at was network efficiency. Now, what gives us more efficiency? Where can we curtail less or maybe connect more generation? Turns out that this is where the March grid example became very important in our case study, or just in our analysis, because we actually simulated the network as it stands with increasing generation, and we modeled the 2 principles. So we modeled last in, first out, and we modeled pro rata, and it actually came out that to achieve lower levels of curtailment, we could actually connect more in a pro rata scenario. So that was one thing that was interesting. The second criteria was, say, fairness, because we, as a DNO, have to treat all of our customers equally, and we have to be fair. However, fairness is very subjective. So you could argue that last in, first out is fair because, I came first, therefore I have a right to a firmer network connection. But you could also argue that fair is, you're curtailing everyone equally, so everyone takes the same hit. Simplicity, we do need to implement this, so we can come up with very complex ideas, but in the end, we need to be able to implement it, and we want to implement it now. And we also want our customers to understand what we're doing. And if we're going to put up a connection agreement in front of them, we want it to be as simple as possible. Learning, it's important because the Low Carbon Network Fund is a research and development initiative. And so anything that can contribute to learning to all of the DNOs, to Ofgem, to all the parties and all the stakeholders, it's important to explore new alternatives and not just stay with this is how things have worked always. And then finally, certainty. And I think certainty is probably the most important, especially to our clients. The good thing about last in, first out is that you can give certainty to a developer that any generation that comes after is not going to affect his curtailment. So whatever he experiences, it probably won't get worse if anybody else comes and connects. However, with pro rata, and we're very keen on understanding how can we actually implement pro rata curtailment, in pro rata, you have kind of that open-endedness that you could say, well, you're curtailing everyone the same, and so let's just keep connecting more and more and more. But it has to reach some level when you say, okay, enough. And this is kind of that tolerable level of curtailment. So it was thinking about certainty that we decided, okay, well, we want to do pro rata curtailment. We have our case study. We have we have a list of potential customers. And how could we, in a reasonable time frame, implement pro rata curtailment? So essentially it means how do we put a limit to how much we connect? The first idea we had was time vintaging. So can we open a gate, like a time gate, and say, okay, from January to June 2013, we're receiving connections, and anyone who connects within this time frame or accepts a connection will get curtailed pro rata. And there were clear disadvantages of this, of saying, well, what if we get too many connections? If we get too little, it might be great, because then they probably won't get curtailed that much. But if we get too many, will it be essentially saying, the curtailment levels are going to be unreachable? So we discarded that. The idea of a capacity auction came up and said, well, why don't we just ask our developers what level of curtailment they're willing to take? They know their finances. They can probably come up with a reasonable number. However, for the time frame that we had, we also thought that we don't have enough customers to actually make it a competitive process, and it certainly would not be keeping things simple. And finally, we kept coming back to this thing of saying, well, how can we set a limit? Just say, this is the amount of megawatts of interruptible capacity that I actually have. Can we come up with an amount of megawatts that's reasonable? And so the first idea we had was, well, why don't we just take a view on what is a reasonable level of curtailment? And we tried to do that, but it just had a lot of, it meant the DNO taking a view on kind of the finances of the projects of our customers, and we decided that really wasn't the way to go. And we finally got to the idea of saying, well, can we think of curtailment in more of the way that the customers will look at it? And essentially, the customers will look at curtailment as lost revenue. And so there is kind of that cost per megawatt of curtailment. So if we are to compare that cost of curtailment with an alternative cost of reinforcement, can we come up with just a sound methodology to determine the amount of megawatts to connect under a constraint? And so this is how we came to the concept of the capacity quota. Now, this graph is really basic economics, and thinking, if in the x-axis I have megawatts connected, and in the y-axis I have cost per megawatt, I essentially have two costs to compare. The first one is the red line that's going up, which is the cost of curtailment. What this line essentially says is the more megawatts I connect, the more expensive it becomes, just because I'm curtailing pro rata. So the more megawatts connected, the more each generator will get curtailed, which means more revenue loss they'll have. So the more generation connected, the more expensive it is for the generators to get curtailed. However, at the same time, and again, this is why March Grid became such an interesting and good example for us, is that, as Satiris mentioned, in the March Grid, there's that the constraint is essentially the transformers. And there is a kind of network plan that could imply upgrading those transformers. The cost of that is about £4.1 million. And essentially what we thought, well, if you could compare the cost of paying for that reinforcement in a, again, pro rata way, you could eventually hit that point where those two lines cross. So the line going down essentially means the more megawatts I connect, the less expensive it would be to pay for the reinforcement if everyone were to pay for it equally. So like that, we came up with this methodology of how to determine how many megawatts we think is a reasonable amount of megawatts to connect, where developers or generators would actually prefer the cost of curtailment than their cost of paying for the reinforcement. So we did this analysis and we came up with the numbers, and then we had the challenge of saying, okay, well now let's set up a set of rules so we can give these developers an offer. And essentially what these rules are is, one, if you come and connect, so essentially these generators have their business as usual alternative, it's more than £1.2 million, and go connect a single sole use asset to somewhere else in the network, or connect to FPP. Now the rules to connecting to FPP are, anyone who is already connected to the network will be grandfathered. So we're not going back to generators that are already connected within that network and saying, let's reevaluate your connection agreement, because we can't do that. So that's kind of rule one. The second thing is, anyone who comes and connects now is an FPP customer, and we will connect them onto the active network management scheme. So essentially, they'll be subject to active network management, and we will be curtailing them. Third rule is principles of access. Everyone who will be connecting behind this constraint will be subject to pro rata curtailment. The fourth thing is the capacity quota. So we will set a limit of X amount of megawatts by which you will be within that block, and we will curtail you pro rata. Then the fifth thing is that we will take responsibility of managing this quota, and when we reach it, we will let you know. And anyone who connects after, because it's, I guess, the big question, right? What happens when we reach that? So anyone who connects after the quota will get curtailed first. So essentially, we go back to the last in, first out, but after the whole block of megawatts pro rata have been connected. Now, we've had the challenge to actually take these principles and put them into a connection agreement. And I think it's been an excellent exercise, because we've worked with the legal department in understanding what is it from a connection agreement which a connection agreement is pretty standardized, what is it that needs to change, or what are the concepts that aren't there yet that we need to introduce. And I think it's important, and it's been an important milestone to actually present these concepts and start talking about them and get customers comfortable with the idea. Because if Satiris showed that map where you have red spreading out into the east of England, we need to kind of have that in mind and know that generation connected to the distribution network is increasing, and we'll have to kind of address that. So there's kind of four concepts that are in this connection agreement, and one of them is curtailment, so essentially limiting generation output. The second one is the constraint. So we actually, because kind of a block or a quota is subject to the same constraint, and it is these generators that are feeding into that constraint, we define physically what the constraint in the network is. We also have a concept of the maximum interruptible capacity. So essentially, it's saying whatever we declare as your maximum interruptible capacity, it's what will be able to control or actively manage. And finally, there's a capacity limit, which is essentially the megawatts that we commit to not connecting anymore before we start doing, within which we do pro rata curtailment. So that's great, and we've actually come up with our connection offers, and Sotiris will later in the day just kind of give you some examples of what we've been offering. But throughout this whole process, and it's been a lot of thinking, and I'm summarizing here in 15, 20 minutes what we've been working on for like 8 months. One of the questions that have come up and that we still kind of need to get our heads around is, well, because we're talking about reinforcement, we all want to understand, well, then when does reinforcement happen? And how can we do our reinforcement and our network kind of operate it more optimally? And so there's essentially 2 things that can trigger reinforcement. The first one, which is pretty straightforward because we're used to that, is the demand triggered reinforcement. So load growth, as we develop and there's more generation demand in a certain part of the network, eventually it gets to a point where we have to reinforce due to demand growth. Now, in the case of that happening, our generators would probably benefit because UK Power Networks would take on that reinforcement, and the generators could probably come back and say, I want to reevaluate my connection, or kind of see if now I'm in a position to not have an interruptible connection, and we'll probably have to deal with that at that time. And then there is the generation-triggered reinforcement. So it would come a moment when an extra generator comes and requests a connection there, and the minimum cost scheme at that point would actually be reinforcing the network. So that would be the case in which potentially we would drive reinforcement triggered by generation. So just to summarize, I think it's important to point out 2 main challenges that we've had throughout these 8 months, and that have been very positive and challenging at the same time. The first thing Sotiris was very clear about, we had our program set out, a project for 2 years, and we understand that unless we actually try our technologies with real customers, the project is unlikely to be completely successful. So we had the task to engage with our customers, because we had real customers in the trial area with real projects that fit exactly what we needed to be able to try our technologies. And we have that regulatory framework in which we have to stay to offer something immediately. And the other challenge that we've had that has also been very enriching for the project is that we've had to work with all our internal departments so we can make this a kind of business as usual process, and that we can have these discussions also within the business. So we had to interact with